Okay, I thought I would take a second here and record another video just talking about quantities and their uncertainties. Okay, so just to put the video in context, I've just finished grading experiment number 3. I thought it might be good to sort of talk about some of these topics, and this seemed to be the easiest way to put it out there in a way that you guys could maybe refer back to in the future if you need to, sort of as a reference. Okay, so I'm going to talk about the way I think about these quantities sometimes. So one useful way to think about these quantities is to break these quantities up into 3 different categories, and I'm going to talk about those in a moment. And I'm going to be talking about all these quantities by referring back to things that we did in experiment number 3, and sort of hopefully the way that you thought about it, or if you didn't, at least the way that you might want to adjust your thinking to sort of get a better handle on some of these things. Okay, so maybe just to start off, sometimes I find it useful to think about these quantities in 3 different categories. Okay, so any of the quantities that we're dealing with in these labs, for example, the length of anything, or time, anything that we're measuring, anything that we're calculating, any known values that we're getting, I find it useful sometimes to break them up into either measured quantities, calculated quantities, or known quantities. Okay, so I'm going to start off by talking about what I think of as measured quantities. And so measured quantities to me are any quantity that we're actually actively measuring in the lab. Okay, so if we pull out a meter stick and we're measuring some length, that's a measured quantity. If we have a stopwatch and we're measuring some period of time, that's a measured quantity, and so forth, right? So how does this differ from other quantities? Well, I'm going to talk about calculated and known quantities afterward, but just when you're thinking of measured quantities, think of anything that you're actively measuring in the lab, okay? So for any of these quantities, we're recording something as we're measuring these things, right? Like either we're making one measurement and that's our quantity that we're going to be working with, or we're making a number of different measurements and then adding them up and taking the average. Whichever way we do that, somehow we're measuring these things and we're recording our measurement, right? So maybe the first distinction here to make is that with measured quantities, you can either have single measurements or multiple measurements, okay? If you're doing a single measurement, and a good example of this would be the way that you should have handled the length of the pendulum in experiment number 3, you were meant to only measure it once. And if you're doing only one measurement, you don't need to build a table for this, right? Like some people built a whole table. They had trial 1, trial 2, trial 3, and so forth. And for each one, they had length or something, and they just kept on recopying. Let's say it was 180 centimeters or 1.8 meters, something like that. Let's say they just kept on recopying the same value over and over, right? And you don't need to do that, right? So maybe I'll just get rid of this. You definitely don't want to be doing that. If you measure a quantity once, take that measurement, write down what that measurement was. So you make a single measurement, you write down L equals 1.800 meters. That's your L for all time for that trial. You don't need to make a whole table for it, okay? Things that we measure multiple times do require tables. So for example, again, to think about what we did in experiment number 3, we're taking multiple measurements for this quantity T, right? So let's say we had trial 1. Maybe I want to be careful because I don't want to use capital or lowercase t. Trial 1, trial 2, 3, 4, and so forth, right? We were supposed to do 5. And then we did the average or whatever. And so for these trials, you were getting some time t in seconds, right? And you'd have some error attached to it or whatever, right? So let's say you were doing this measurement. I don't know, I'm just going to make up some numbers here, and you measured maybe 25.26 seconds and 25.14 seconds and so forth, right? So you have a table of things that you're building up. That's great. You're doing multiple measurements, and that's fine. So this is really all just to demonstrate this distinction between something you're measuring once and something you're measuring multiple times. But be careful here. We're talking about the t that we measured, right? The small t. We're not talking about the big T. The big T is a calculated value that we get from measuring the small t, right? We're measuring the small t, which is which was the length of time for the pendulum to oscillate 10 times, right? We then, from that value, generate big T, okay? So I'm going to talk more about big T when I come to the calculated quantity part. But for the measured quantity, big T is not a measured quantity; it's a calculated quantity. We propagate the error into big T. We don't measure big T. We measure small t. Okay. And so for any measured quantity, whether it's a single measurement or a multiple measurement, we need to have an entry in an error analysis table. So I took the time to draw this really rudimentary error analysis table down here. And basically what we need to do is we need to enter in an entry for any measured quantity. So any measured quantity has to have a column in one of these tables, right? So here we have our capital L length and our lowercase t time. And so what would we do? Well, we'd enter in the values in the appropriate fields here. So for example, we know that our instrumental error for a meter stick is going to be half a millimeter, right? Say we had some observational error, I don't know, 2 millimeters or something. Then we know that our total systematic error is just the total of these two values, right? And since we did a single measurement, only one measurement, we don't have access to statistical methods to examine this error any further. There is no standard deviation. You can either do NA here, you can just cross it out, whatever you want to do with it. But there is no standard deviation. There is no random error. Okay, so we don't have access to statistical methods because we really only made one measurement, and so the only MPE we could use is our total systematic error. So we simply bring down our total systematic error, 0.0025, and then you can make a note about rounding this. Let's say you had made this measurement up here. So we made the measurement of L is 1.800 meters here. So then I would end up rounding this. I would say rounded to 0.00 say 3 meters, right? And so this is it. We now have our L. It's a measured quantity. It has an error or an uncertainty attached to it. So now you can write down L, which is now 1.800 plus or minus 0.003 meters, and this is our L for all time now. Okay, so we have this measured quantity. That's it. That's our L. We're moving forward with L with that value. Okay. For T, it's slightly different. For T, again, we can write down things like the instrumental error. The instrumental error on the stopwatch is just one tick of the smallest sort of time scale. We can write down our observational error, whatever you think is appropriate here. Maybe something like that. You get your total systematic error. That's great. And now, since we've done multiple trials, we can apply all these statistical methods to analyzing whether our error makes sense here. And so I'm not going to go through the whole thing in detail here, but this is where the random error and the standard deviation calculations come in. The formulas for this are all laid out on page 11. So all this stuff you can find on page 11 and 12 of the lab manual. And maybe I'll just very quickly write down what the equation is in case you want to use this as a reference in the future. But if you want to find the standard deviation is simply this equation here. And I'm going to sort of unpack it in a second. Okay, so what are we doing here? Okay, so what is n, first of all? N, and I'm not going to write these all out. This is all laid out in detail on pages 11 and 12 of the manual, but I'm just going to talk through it really quickly here. So n is the number of trials that we did. In the case of our T in our lab number 3, we did 5 trials. So our n would be 5. We're going to be summing up the difference between each individual trial and the average trial and squaring it. as this part of the equation here says, for each of these entries. So we're going over from I equals 1 all the way up to I equals n. So for each entry, we're taking the entry, we take away the average. So the average would have come from up here, right? We just add up all these and divide by the number of trials. We take the average away from each individual trial, square it, add it to the next one, the next one, the next one 5 times, right? We then divide the whole thing by n minus 1 as this term would suggest, okay? Take the square root of the whole thing, and that's great. You end up with your standard deviation that goes up here, okay? That's fine. Your standard deviation ends up there. Your standard deviation is a useful tool, but it's not going to give us our MPE. It's just going to be a step on the way to getting our random error. Okay, so once you have your standard deviation, you're then only one short step away from getting your random error. So I'm going to write the random error like this, but sometimes it's written as SEM or random error. And I'm just going to rewrite it again. And the way you get your random error is you just take your standard deviation and you divide it by the square root of the number of trials. Okay, so in this case, we would just take our standard deviation that we calculated a second ago, divide it by the square root of 5, because we have 5 trials. That is your random error. Okay, so your random error is a number that goes in here, some number. This was a different number that went up in this standard deviation, right? So, but once you have a measurement that you're making multiple times and you have access to statistical methods, in this lab, the way we handle using this is we then take the greater of either the total systematic error or the random error. Okay, I've seen a lot of people adding these two together. It's not the total of the two. You look for which one is larger. So I'm just going to make up a fake number here. I'm going to say that our random error ended up being something like 0.08 seconds, and this standard deviation would have been something somewhat larger. Say it was 0.25 seconds or something. Okay, so whatever that was, and again, these are not correct. Like, I'm just making them up on the spot. So if you divided 0.25 by the square root of 5, you probably would not find it was 0.08, but that doesn't matter. Basically what I'm saying is you need to calculate these two numbers, and then we're taking the greater of the two of these. It's either, your MPE is either going to be your total systematic error or your random error, whichever one is greater. That's what we're doing in this lab. That's how we assess what our MPE is going to be. In this case, the MPE is going to be 0.11 seconds, okay? And so now, as I said before, we have our small t. Our small t, and I'm just going to make up a number again. Let's say our small t is, I don't know, 25.12 or something, plus or minus 0.11 seconds. Okay, that's the small t we're going to go forward with. These are the only two measured quantities in the lab. These are the only two that need to have entries on our error analysis table, right? So once we have the two of these, that's it for measured quantities. The next quantity that we want to get on our way to getting G, and again, I'm talking about all this in the context of experiment number 3, but so remember, well, okay, maybe I'll step back and I'll rederive the formula, but basically, we're starting from this formula for the period of our pendulum, written in terms of the length of the pendulum and gravitational acceleration, right? So we saw that this gives us, squaring both sides, we saw that this gives us, right? And if we wanted to isolate G, we can do that. And I'm going to write it again in a pretty suggestive way here, so that we can see, so that we can sort of see really how we're going to want to do this error propagation later. And maybe I'll talk about that in a moment, but not for right now. I'll even put in this power of 1 here, which is just sort of implicit all the time, right? So that's our expression for G. Now, we have L, but we have lowercase t. We need uppercase t. We need the period to be able to calculate G. But we get to capital T not by measuring it, but by propagating the error from little t, by calculating from little t to big T. The calculation is very simple. We know that big T is just little t over 10, right? Because there was 10 individual oscillations in each of our collections of 10 oscillations. So we can easily find T or big T, our period. Also, by looking at, and I'm going to get the page for you here, by looking at the bottom of page 15 in the lab manual, there's a number of equations given to us there. So, page 15, bottom, equation, so there's an equation under the heading E.2.2, error propagation rules for other equations, and we can see that for some quantity, 1 over k, a plus or minus delta a, this really, so doing this multiplication gives us ak plus or minus delta a, oops, and this should be over. Okay, so this is sort of just a fancy way of saying that really we just divide the error that we got also. So let me just get another page going here. So really this is just telling us that well, we had our t, so let me copy down t here. T equals 25.12 plus or minus 0.11 seconds. Okay, so if we want to get t, well, that was easy, right? We just divided t by 10, so we ended up with this number, right? But if we want delta t, it's just as easy. We just take our delta t from here. This is just delta lowercase t. We just take our delta lowercase t and divide it by 10 also. So we end up with 0.011 seconds, right? And this together gives us our capital T as a calculated quantity, right? So what we're doing here, this is just a very simple error propagation. We're just propagating the error from our expression in lowercase t to our expression in uppercase t. So we now have a t which is equal to 2.512 plus or minus 0.011 seconds, okay? And we have our period now that we need to use in the equation that we have for g, okay? And so t capital T, our period, this is a calculated quantity because we're propagating error. For any calculated quantity, we need to be doing some kind of error propagation. We saw a very simple error propagation here, but g, which I'm going to rewrite the expression for here, is also a calculated quantity. Okay, this is our expression for g. We're going to calculate what g is from L and t, which we both have. We have t right here, and we had L above here, right? So we have L and t. We can calculate g. We can easily calculate what g is by just plopping in the base value for L and t, but we also need to propagate the error. G only makes sense if we propagate error as well. So we can easily calculate what g is. Our g would simply end up being 4 pi, this should be squared, and our L would end up being what, 1.800 meters, and our t, well, we see our t right there, seconds, and that's great. And this should come in with a minus 2. And again, I'll put the power in here, just even though it's always implicit, but just so we can see it there. And so we can easily calculate g, but we also need to do the error propagation. Now there's a number of ways to do error propagation, right? In this lab, in lab number 3, in this experiment, we were supposed to do the error propagation using the equation method, okay? I put a separate video up on the equation method where I describe how to do the equation method for this very example here. So take a look at that if you're not clear on how to do that. But again, the expression for that is just going to end up being delta g over g squared is equal to 1 times delta L over L all squared plus minus 2 times delta t over t all squared, okay? And if you want to know where I got that from, just look at the other video. But once we do this, once we solve for this, we need to manipulate stuff a little bit. We need to take the square root of both sides and multiply out g, but we're only looking for delta g. Once we do this technique, we're then able to write down g as whatever it might have been. I'm just going to make up some number here. Let's say it was 9.52 plus or minus, and now we get our delta g. That goes in here, and we have, say, I don't know, some value like this, right? Meters per second squared, okay? And so this is, again, an example of a calculated value. This doesn't need an entry in your error analysis table. It's a quantity that we're calculating, and we're propagating the errors from the measured quantities that we had earlier into these quantities, right? So we're getting this g by using the values that we measured and propagating the errors for those values into this g. Okay, so again, calculated value. And then finally, just to talk really briefly about the known values. These are values or quantities that we don't really come up with in the lab. These are things that we're given. So a known value would be, well, the value of g that we're given, right? So let's say this was like g1 for your first trial or whatever. The sort of widely accepted, or the known value of g at whatever the parameters that we're taking here are, well, the known value is, I should say, right? And so this is the sort of value that you're given. You're always going to be given a value that has some uncertainty attached to it. Right here, all of our values have to have uncertainty attached to it. And let's say that this was the g that we calculated in our first trial, and this was a g that we know is the actual g at our elevation at this point on the Earth, right? Let's say we wanted to compare these two. So we have these. Well, let me take a quick step back before I talk about comparing these two. So we have these three types of values, right? Measured quantities. These are things that we're actively measuring in the lab. Calculated quantities. These are quantities that we build out of measured quantities, that we don't actually directly measure, but we build from these measured quantities before. So for example, measured quantities, thinking about lab number 3, that's L and small t. Calculated quantities, that's big T and G, right? So G1 or G2 or whatever, the G for the L1 or 2 that we had, like the length of the pendulum, and then the T's that we got. So basically you would end up with, here, let me just quickly rewrite this. So what you would end up with is you had some L1 that you measured, the first length. You had some L2 that you measured. You had some small T1, like the 10 oscillations in the first set of trials, and you had some small T2. The calculated quantities that you would end up with would be T1, big T1, and big T2, as well as G1 and G2, right? Like the two gravities that you calculated. But the known quantity that you'd be comparing all this to is a sort of G at our elevation, the known value for G, right? So thinking about all these things in those terms, measured, calculated, and known, let's say we then wanted to calculate, or I should say compare the calculated values for G1 and G2 to the known value for G, right? So always in our summary, in our conclusion, we want to write down our findings. We want to write down, so let's say this was G1 that we found here. I definitely want to make sure that I have this value of G written in my conclusion. Well, okay, so whatever. I mean, I'm not going to write the whole conclusion out here, but basically, imagine you had your conclusion here. You would definitely mention G1. You would also mention whatever your G2 was, some value, and then you want to make some comment about whether or not they agree with an experimental uncertainty to whatever it is you're comparing to. So in this case, to the known value of G. So let's just do G1 compared to G here. So we want to see if either of these, well, if these values overlap. So the easiest way to think about this is just think about a number line, right? So just think about the real number line, and you can imagine that again, that G sits somewhere on the number line here. G equals 9.81, but G is not as simple as just being a single point on the number line. G we can think of as a sort of blurry region on the number line. It has this plus or minus 0.1. So we can imagine that somewhere out here and somewhere out here will be 9.80, and 9.82, right? So our G can exist anywhere in this region, this blurry region, right? So we have a central value, and then we have the other values that are sort of at the extreme edges of its allowable experimental error. Okay, then we have our G1, right? So I can put G1 in somewhere, say over here. We'll call this 9.52. Excuse me. So we'll call that 9.52. And now this has a somewhat larger blurry region, right? We have a larger 0.22 blurry region. So how large can it be? Well, 9.52 plus 0.22 will give us 9.74, right? So that would end somewhere like here, let's say. So 9.74, and it'll extend all the way down here to 9.30, right? So we have a large blurry region in here on our number line. And if these regions were to overlap, then we would say that these two values agree within experimental uncertainty. Okay, but since they don't share any region in which they overlap, they don't touch. We would say that these two values do not agree to within experimental uncertainty, and that's really all that there is to it. If the regions overlap, they agree to within experimental uncertainty. If they don't overlap, they do not agree to within experimental uncertainty, and that's really all that we're looking to say in our conclusion. On top of that, we want to make any other clarifications about stuff that we might have done or speculation as to what might have gone right or wrong in the experiment. But basically, we always want to be addressing the question of, did our findings agree or not agree to within experimental uncertainty with whatever the known value we're looking for is. Okay, so this is just quickly a sort of sum up of my thoughts on quantities and their uncertainties. We really want to make sure that we're differentiating between measured and calculated quantities, and when we're thinking about measured quantities, we want to be differentiating between single and multiple measurements so that we're doing the right stuff with these things, right? Measured quantities need entries in error analysis tables. Single measurements don't have standard deviation or random error. They can't have these statistical methods applied to them. Multiple measurements do. They need to have those associated with them. We have to remember how to get our MP. It's the larger of systematic error or random error. Then once we have these things, we need to write down our measured quantities in their sort of final forms, and then use those measured quantities to calculate our calculated quantities. As we did here, we're taking L and small t. We're then calculating big T from it, and then further we're calculating G using big T and L, which we had before. And then once we have G, we write down G and we propagate the error in G using whatever error propagation method we need to. So here we saw a little bit of the equation method. We also saw some very simple sort of application of other equation methods. There's other tools we have at our disposal, like the brute force method, but generally speaking, we only use the brute force method when we're told to in the lab, and that's usually because it's too difficult to apply the equation method for this type of a lab. Okay. And so again, this is just a quick sum up of my thoughts on these quantities. Please let me know if you guys have any other questions, and I will leave it there for this video.